So we are now going to look at two simple and very similar derivations. Number density of electrons in the conduction band and in the valence band. So first we will be seeing the conduction band. So number density of electrons in the conduction band is basically how many electrons you have in the conduction band, because like I said, when you supply energy, an electron hole pair is generated. So there is one electron and one hole, let's say, then this free electron is what is going to contribute to conduction of electricity. The electrons which are in their positions in the valence band, they are held together by strong attractive forces, so they will not be able to break free from that force. It is the free electron which is capable of carrying electric charge, and therefore it is the free electrons which are responsible for conduction of electricity. So if I want to know how many electrons are contributing to conductivity, I need to know how many electrons are there in the conduction band. So that is what this derivation is going to help me find out. Now if you remember from your quantum chapter, the number density of electrons is given by this formula: integration number density of states into probability that it is occupied by an electron. So what is this? In the quantum chapter we learned that energy levels are quantized, meaning there are specific energy levels and only those can be occupied by electrons. An electron cannot exist anywhere it wants. So if you want to know how many electrons are present from a certain energy level to a certain energy level, you first need to know how many allowed energy states are there between the two limits, and then what is the probability of those states being occupied by an electron. So that's exactly what we do here, the limits being from EC to infinity, where EC is the start of the conduction band, from there upwards up to infinity. So what are we trying to find out here? How many electrons are present in the conduction band. So from the start of the conduction band till infinity, how many allowed energy states are there into what is the probability that they are occupied, and we integrate it between these limits. That is integration from EC to infinity, G of E, F of E, dE, where G represents the number density of states and F is the probability of its occupation. Now before we start doing the integration and all, let us recall what is the F of E function. It is 1 by 1 plus e raised to e minus EF by kT, where K is a constant, it's the Boltzmann constant, T is the temperature in Kelvin, E is the energy level which you are looking at, and EF is a reference level which we call the Fermi level. So what exactly is the Fermi level? We learnt more about it when we were doing quantum. So this is the expansion for F of E function. Now this whole e to the power term, it's going to be very large. It's almost going to be close to infinity, because we are looking at a large interval from EC up to infinity, right? So you're dealing with a very big set of energy levels. So this term is going to be very large. So adding 1 or dropping the 1 does not make a big difference. So we ignore the 1 for the purpose of simplicity in calculation, and we take 1 by e raised to e minus EF by kT, which is nothing but e raised to EF minus E by kT. So because it's in the denominator, when it goes to the numerator it gets a minus sign, so minus of E minus EF would be EF minus E. So what have we done here? We haven't started integrating yet, we just looked at the F of E function. This is the function. Because this exponent term is a very large term, it is not going to affect our result much if we drop this 1. So for simplicity's sake we dropped the 1, and then when this goes to the numerator it becomes e to the power EF minus E by kT. So with that expression for F of E at hand, we perform the integration of G of E F of E dE, 4 pi upon h cube to me star whole raised to 3 by 2, integration between limits EC and infinity, root over e to the power EF minus E upon kT dE. How did I come up with this equation? So this expression for G of E again we derived when we were studying quantum, and the expression for F of E we just simplified a minute ago. So when you put both together, this is the final expression you get: 4 pi upon h cube to me star whole raised to 3 by 2 integration from EC to infinity root e to the power EF minus E upon KT dE. This is the expression we have. We simply substituted whatever expansions for G and F we already knew. Now, this is somewhat similar to a standard integral we have, but the limits here are from 0 to infinity. Here it is from EC to infinity. So if I am able to transform these limits from EC to infinity into limit 0 to infinity, then this expression resembles this expression. So I can immediately substitute this as the answer without having to actually perform the integration. So this is one of the predefined integrals which has been mathematically computed, and it is given to you as a formula. You don't need to compute this and prove it, or sort of, you don't need to perform the actual integration if your expression is of this form. Our expression is quite similar to this, but the problem is the limits. So what we do is we try to transform the limits from EC to infinity to 0 to infinity. How do we do that? Wherever you have an energy term in the limits and in the expression inside, you subtract EC, because EC minus EC will become 0, and that is our goal. So infinity minus EC is still going to be infinity, because infinity is a very large number. EC minus EC is going to become 0. So we transformed our limits. Inside, E becomes E minus EC, e to the power EF minus EC minus E minus EC upon KT. So this is a step where a lot of people have a doubt about why this is happening. So the thing is, we have a standard defined integral at this point. We want to convert our term, our expression, to match this format for the sake of simplicity in calculation. To do that, we are transforming the limits. So what I ultimately want is this EC should become 0. So I am subtracting EC from here, which means wherever else I have an E term, I have to subtract EC from all of those. So when I subtract EC everywhere, this is the expression I get. So with that out of the way, it's very simple. Now the limits are fixed. It's 0 to infinity. This is root over E minus EC, e to the power EF minus EC minus E minus EC by KT. Now EF and EC are both constants as far as we are concerned, because we are integrating with respect to E. So the EF minus EC term is taken out. The only part which is of concern to us is e to the power minus E minus EC upon KT dE. So now what we have, this entire thing is a bunch of constants. Integration from 0 to infinity, root over something, e to the power the same thing divided by KT. That's what we have. So if you look at this standard form which was given to us, that was again integral from 0 to infinity, root over something, e to the power minus a times the same thing, dx. So by comparing, we can see that x is E minus EC and a is 1 upon KT. So this matches the format of this integral. So we know already that the solution for this integral is this, it's a given. So we simply substitute the corresponding values from here. So it is pi raised to 1 by 2 divided by 2 a power 3 by 2, where a is 1 upon KT. So what is the solution is this entire bunch of constants, pi raised to 1 by 2, KT raised to 3 by 2 upon 2. So you rearrange all the 2's, 4's, everything you put together. Finally, this is what you get. And what were we actually trying to find out? Number of electrons in the conduction band. So that is what we did this entire derivation for. And this is the final expression. 2 pi me star KT upon h squared whole raised to 3 by 2 e to the power minus EC minus EF by KT. And since this is full of just constants, we replace it by one constant NC. So the number of electrons in the conduction band is given by NC e raised to minus EC minus EF by KT, where NC is a constant, EC is your start of your conduction band, EF is your Fermi level, K is the Boltzmann constant, and T is the temperature. So quickly we'll run through this derivation again. We wanted to find out how many electrons are there in the conduction band. The procedure is the number of allowed energy states starting from EC, the beginning of the conduction band, up to infinity into the probability that any of those states is occupied by an electron. That is integral from EC to infinity g of E f of E dE. This is the expression for f of E. Since this term is e to the power term is very large, we are dropping the 1. It becomes this. Now we are performing the integration. This is the expression we have. We want to bring it to a standard form, so we apply transformation of limits. We subtract EC from every term. We take all the constants out. This corresponds to this form, so we find out what are the values of x and a, and then this is the given solution to us. So we plug in the value of a which we found out. We club all the constants together and name it as NC. This is the final expression we get.